Okay, let's dive straight into this explainer. I want you to imagine your Cambridge computer science exam is, well, kind of like a high-stakes Formula One pit stop, right? Every single second you spend writing and every specific word you choose is either shaving time off your race or costing you critical championship points. You're completely against the clock, the pressure is literally immense, and precision is absolutely everything. You can't just throw on any old tire and hope it works. You need the exact right strategy, and it needs to be executed flawlessly.
Because if you don't have that precision, you're going to be looking at this number. 0. Look, this 0 is exactly the number of marks you'll get if you write a generic, untargeted answer under that exam time pressure. And yeah, that's even if you vaguely know the concept. This is literally the most painful mistake we see. You spend hours revising, reading the textbook, memorizing those vague definitions, but then you get into the exam hall, face a complex scenario, and write a generic answer that just totally misses the mark scheme. So we're going to change that reality for you today.
All right, Lap 1, Core Computing Algorithms.
We're going to fix that 0 immediately by upgrading your foundational engine, which is the computing algorithm concept. The crucial point here is that software relies on algorithms to essentially bridge the gap. They tell the physical hardware exactly how to solve a user's problem. When you're programming software, you aren't just, typing words. You're constructing a highly specific set of instructions. This is exactly how software begins its existence, taking human logic and translating it into a sequence the physical computer systems can execute. The examiner absolutely wants to see that you understand this precise relationship.
Now, to process all that complex data, algorithms often need to handle different data types. A really common one is the floating point number. A floating point is simply a number in programming that contains a decimal point. But here's the clever bit. That decimal point can dynamically float around into different places. This is a total game changer because it allows the computer to efficiently manage really large or super small values without breaking the whole system. It's an essential tool in algorithmic thinking for sure.
Moving right along to Lap 2, Algorithmic Searching. So what's really interesting here is how we apply these instructions to actually find data when we're under pressure. Let's look at a fundamental method, the linear search. Just like the name implies, in a linear search, the algorithm looks at every single item of data in a set, in a strict sequential order. First item, then the second, then the third, and it just keeps going until it gets an exact match for whatever it's looking for. Once it gets that match, boom, the search is complete. It's systematic, it's super reliable, and you absolutely need to be able to explain this exact step-by-step sequence to secure those marks.
But here's where the stakes get a bit higher. I mean, it's one thing to search for data locally, right? But what happens when that data is moving? In just a moment, I'm going to show you a hidden examiner clue that will completely change how you answer these questions. But first, you need to understand exactly how algorithms verify that data hasn't been corrupted during transmission.
Which brings us to Lap 3, Error Checking Protocols.
Let's see how error checking builds a literal safety net around your data. This brilliantly illustrates the difference between two major protocols, so pay close attention here. On the left, we've got the checksum. This method relies on an agreed protocol that's determined prior to the data transfer. Basically, an algorithm calculates a checksum value using math on the data being sent. The data and that checksum are sent together. The receiving device then uses that exact same algorithm, recalculates the value, and compares the two. Match? Success? If not, it asks for a retransmission. Now look at the right side, the echo check. This is entirely different. There is absolutely no prior agreed protocol here. None. Instead, the receiving device just immediately bounces a copy of the exact data it receives straight back to the sender. The sender then does the comparison. Understanding this specific difference, the mathematical protocol versus the simple bounce back, is exactly what the examiner is looking for.
All right, Lap 4, the high mark framework. We've reached the most critical part of our pit stop, turning these technical concepts into maximum marks on your exam paper. I need you to memorize this 4-step framework. It's basically your cheat code for the mark scheme. First, state the correct technical concept. Second, pull evidence or data directly from the question's scenario. Third, give the scientific or computational reasoning, the how and why it works. And finally, make sure you're using the exact examiner wording, the specific terminology they demand. Let's actually see this in action.
Time for the Pause and Solve challenge.
Imagine you're asked to design an algorithm for a train system to determine the correct passenger fare. Try to spot the error here. Go ahead and pause this explainer for a second and really think about it. Why does an answer that just generally says the algorithm will input the passenger details and calculate the cost of the ticket fail the Cambridge mark scheme? What's missing from that answer?
Okay, here is that hidden examiner clue I promised you. The flawed answer on the left is way too generic. It totally ignores the context of the scenario. But the upgraded answer on the right? That secures the top band grade by explicitly using what we call scenario nouns. To get full marks, your algorithm must explicitly mention that passengers could be adults, or require concession fares, or be children. You have to use the variables provided in the specific context. If they give you a train scenario, your variables shouldn't just be X and Y. They should be adult ticket or concession rate. Tying your technical knowledge directly to their specific scenario nouns is the absolute secret to high marks.
Almost done. Let's do a quick recap on command words.
Your strategy has to adapt based on exactly what the question is asking. Let's look at these Cambridge command words. If they say define, give a precise textbook definition. If they say describe, outline the steps, like how that linear search works. If they say explain, you need to provide the reasoning, the why, like why a checksum caught an error. If they say compare, highlight the differences, just like we did with the echo check and checksum. And always remember, 1 mark normally needs 1 distinct technical point. Don't repeat yourself. Tailor your response directly to these command words. Use those scenario nouns, and you're going to absolutely crush this paper.
So, you've mastered the fundamentals and the high mark framework, but your pit stop isn't quite over yet. Paper 2 is absolutely full of programming traps, tricky logic gates, and database queries that are literally designed to catch you off guard. To make sure your next lap is flawless, you definitely need to watch our next explainer on common Paper 2 traps. And hey, don't forget to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to completely excel in your Cambridge exams. So what trap are you going to disarm first? I'll see you in the next one.